All right. Now there's kind of two subtle ways that the multiplication rule can be applied. And the two ways that I've noticed, is two events can be applied using the multiplication rule simultaneously or sequentially. So let me tell you what I mean by simultaneous. So let's look at an analogy. So imagine a student goes to a farmer's market wanting a plum and an apricot. So one would naturally think that the student would end up buying two fruits, one plum and one apricot. So when we use and kind of in everyday language, this is kind of the context that we use it. A student wants a plum and an apricot. That means they're going to go and buy one plum and they're going to buy an apricot. However, the word and has a different meaning in statistics. If a statistics student went to a farmer's market and wanted a plum and an apricot, then the statistics student is expecting to buy one fruit with the DNA of both a plum and an apricot. He's looking for a pluot. So this is the context in which and is being used in statistics. If we were to think of this maybe as a Venn diagram, and here is the Venn diagram of the DNA of a plum, and here's the Venn diagram with the DNA of an apricot, then the intersection of a plum and an apricot, if I could spell, would be a pluot. Okay, the DNA from both, but where both kind of intersect. So let's look at our first example here, looking at the multiplication rule and how it would be applied simultaneously. So a card is drawn from a standard 52 card deck and replaced. Calculate the probability of A intersects C, provided that event A is an ace and event C is a club. So what I've provided here down below is a table that represents all the cards in a 52 card deck of cards. And so let's identify event A. So event A is going to be an ace. But I guess actually before we do that, let's first identify the sample space. So the sample space is all possible outcomes in a 52 card deck, which would be all of the cards, all the numbers and all of the suits. Okay, so event A is going to be the event where the card is an ace. So that's going to be all of these here. That is event A. And then event C is that the card is a club. Okay, so all 13 of these cards are clubs. That's event C. And the intersection, let me use a different color to help you. So the intersection is where those two events intersect, where they overlap, which is right here. So, just by looking at this, we can see that the probability of A intersects C is going to be 1 out of 52 because there's only one card out of 52 that is both an ace and a club, an ace of clubs, right? Again, I'm choosing a really simple example to help you learn the math behind all of this. So that's kind of what I just wrote here in this first sentence. So looking at the Venn diagram above, there's only one card, which is both A and C. Therefore, one would expect the probability of those two events to be 1 out of 52 or 1.92%. Um, and if you went about, applying a test of independence of these two events, and you apply the multiplication rule, then you look at the calculation of the probability of the intersection of those two, that comes out of 1 out of 52. And if you calculate the probability of A times the probability of C, and you multiply those two together, well, what's the probability of A? Well, that's 4 out of 52. So it's 4 out of 52 because A is the probability of getting an ace. And so there's 1, 2, 3, 4 cards out of 52. And the probability of C, which is the probability of getting a club, how many clubs do we have in a deck? Well, we've got 13. So there are 13 clubs in a deck of 52 cards. And 4 out of 52 times 13 over 52 is 1 out of 52. And so the expression on the left equals the expression on the right, and therefore the two events are independent. And since the test of independence passes, we can go ahead and say that this is the probability. All right, now let's look at another example that appears to be the same, but it's going to have different results. So in this example, a card is drawn from a 52 card deck and replaced. Calculate the intersection. And now event A is being defined as being an ace of hearts, a 2 of hearts, a 3 of hearts, and a 4 of hearts. So you can see I've kind of colored in event A here. The one thing I haven't drawn in is the sample space. Let me do that. Okay, that's all possible outcomes. And event C is the event where the card is a 3. So you can see event C is colored in here. And we want the probability of the intersection. Now again, looking at this, we should get an answer of 1 out of 52. And what we did last time is we applied this test of independence. So when we apply that test of independence here, and we compare what we get on the left with what we get on the right of this test, you'll see they don't equal each other, right? So in the previous example, we had a deck of cards with event A and C defined in a certain way, and those two events were independent, and that was our answer, 1 out of 52. But here, when we apply the same rule and we do this test of independence, we don't get the same values on either side. So the way that A and C are defined here, A and C are dependent. So therefore, despite we've had with replacement, the events are defined in a dependent way. Hence, A and C have failed the test of independence. So when two events fail the test of independence, then we have to use this other equation, this other multiplication rule equation, in order to calculate the probability. So we've got the probability of A, which will be the order of A divided by the order of the sample space. And then we have the probability of C given that A occurs first. And that's a conditional probability. And that is equivalent to calculating the order of the intersection divided by the order of A. And the order of A over the sample space is going to be 4 out of 52. And the order of the intersection is 1, right? Because when we look up here, the order of the intersection is 1, and the order of A is 4. And notice here that the 4's cancel each other out, and you're left with 1 out of 52. So the probability that those two events, that an event occurs where those two events intersect is 1 out of 52. And the only way we could have calculated that correct answer was to use this alternate multiplication rule. Had we gone ahead with trying to calculate the probability here and just used this to calculate our probability of that intersection, we would have gotten this answer, and that would have been wrong. And we can see that clearly, by this illustration up here. So you really just have to be careful. You can't assume that, two events are independent. You have to apply this test first. And if it fails it, you need to use this alternate form of the multiplication rule. All right, I think this is a good place to stop. Let me know if you have any questions.